Hi, my name is Alec, and this is my final presentation. It's called Classifying MRI Data as Demented or Non-Demented. And my goal was to build a model using deep learning and TensorFlow that can accurately classify T1 weighted MRI scans as demented or non-demented. So for some introduction, dementia is a syndrome, usually of a chronic or progressive nature in which there is deterioration in cognitive function, i.e. the ability to process thought beyond what might be expected from normal aging. Around 50 million people worldwide have dementia, and every year there are nearly 10 million new cases. Although we don't yet have a cure for dementia, early diagnosis allows optimal management of patients. However, brain scans are time intensive and costly. So how do we solve this problem? And we look to deep learning. So I got the data from the OASIS-2 dataset, which is a longitudinal collection of 150 subjects aged 60 to 96. 72 of the subjects were characterized as non-demented, 64 were characterized as demented, and 14 were characterized as converted, meaning in their first scan they were non-demented, and in their second, or maybe later, they were characterized as demented. So to access and filter the data, I created my own script called download data pi, and the resulting data set was nearly 46 gigabytes, which was huge given my limited computing power. So then I filtered and compressed the data using another script that I made called filter data to make the data more manageable. The resulting file was just under two gigabytes, which I was able to upload to Google Drive and access through Google Colab. And so to filter the data, I did the following things. I removed all the converted subjects because it was unclear at which point they went from dementia-free to having dementia. And then for each subject, I just kept the first scan from their first visit, which just further cut down on the file size. So loading the data and pre-processing. I loaded the MRI data using the NI Babel package using this function. Then I normalized the image to zero mean and unit variance with this function. And then I resized it to a smaller NumPy array. It was originally 256 by 128, and then I resized it to 128 by 128 by 64 with this function. And I resized it because it allowed for faster training and processing speed. And I don't show it here, but then I did a 70-30 train validation split. So I had 136 total images, and then I ended up with 94 train images and 42 validation images. So because all of these images could not be stored in memory all at once, I had to create a Python generator function to continuously load data while the model was training. And then this function was used in a TF data dataset object. And then that dataset object was shuffled upon loading the data and fed into the model with batch sizes of 2. So then I'd wanted to visualize the data, and I created a function that showed a montage of 20 slices. Here's the function, and here's my output. So you see, 20 slices of a single scan. And so then I defined my model, and I created a model based on the one by Zunair et al. In a 2020 paper. And this model is predicated on the idea that a 3D CNN should perform better than a 2D CNN on volumetric data, as there is important information in the depth dimension. A 2D CNN independently deals with individual slices and therefore discards the depth information. However, the problem with feeding into a 3D CNN is that it is much more memory intensive. That's why in the data processing step, I resized my volume from 256 by 256 by 128 to 128 by 128 by 64. And then this downsampling allowed me to leverage that 3D information of the image without overwhelming my computer. So in my model, I had 4 3D convolutional layers, each followed by a max pooling and a batch normalization step. And I finished with a global average pooling layer, then a dense layer with 512 units, and then a dropout layer to prevent overfitting. And so my output layer was a 1-unit dense layer with a sigmoid activation function, which is often used in binary classification tasks. Okay, so to train my model, I decided to use the Atom optimizer, which has proven to be effective in many image classification problems, such as the MNIST digit recognition. But I implemented a slight twist based on the recommendation of the Zunair et al. Paper, and that I set a conservative learning rate, a conservative initial learning rate, and then had that learning rate exponentially decay over the training. And then I used, when I compiled the model, I used a binary cross entropy loss function because it's a binary classification task. And then I used accuracy as my metric, which is pretty standard. And so then I set a callback to stop the training if the validation loss stopped improving. And I set a callback to save the best performing model. So now let's look at the model performance. Pretty much the model didn't perform very well on the validation data. After about 30 epochs, the validation loss stopped improving. And so the validation accuracy on the 30 epoch was actually just over 50% right here. But the best accuracy I achieved throughout training was 69% over here. And because that's the best performing model, that was the one that was saved. And so an important thing to note is the training accuracy kept improving and was actually pretty high by the end, which is a sign of overfitting. Yeah, like the training accuracy kept increasing and the validation accuracy, for the most part, stayed about the same. So then I loaded a single scan from the validation set and loaded the model to make a prediction on that specific scan. So this first one I loaded was from class 0, or the non-demented class. Yeah, and then I loaded the model down here. And actually the model performed pretty well on this specific scan. It was 94% confident that the MRI scan was non-demented, which is correct. And then I loaded another image from the validation set from class number 1, or the demented class. I loaded the model to make a prediction, and it was 86% confident that the scan was demented, which again is correct, but I guess it's a little less confident in that prediction. So in the end, the model didn't perform very well in the validation data, and there's a few explanations for that. So the model was trained on very few data points. There were only 94 scans in the training set and 42 scans in the validation set. After about 30 epochs, the model was overfitted to the training data and needed to be exposed to many more scans to become accurate on the validation set. However, as it was, the model training already took a very long time. 30 epochs of training took about 2 hours for me. This was because I had to use a generator function to load the data. I had to continuously load scans throughout training rather than just access them in memory. And one solution to this problem is to just create a TF records data set. But I just didn't really have enough time to do that. And that TF records dataset allows you to train much faster because you get better use out of your GPU. So TensorFlow takes care of loading more data while your GPU is crunching the numbers in the training. And so as I work to improve the model, that will be my next priority. So the next explanation was that the data itself was flawed. So although I normalized the voxel intensities, I didn't do spatial normalization. So the images probably had all sorts of different orientations. Some methods to counteract that are accounting for voxel spacing by resampling to an isotropic resolution, or registering the images to the same space. And I could also augment the data set, adding noise, rotations, or translations to existing images to expose the model to more examples during training. And that would likely decrease overfitting. And then finally, my model could have been flawed. But because I spent so much time preparing the data and training the model, I didn't really get a chance to play around with the model parameters. So, maybe adding or removing layers, changing the number of filters or units, adjusting the amount of dropout, or changing the loss function could have improved performance. Like for example, I would have liked to try to use the Atom optimizer with the default settings. I had it set with the exponential decay learning rate. and the default settings for Atom have been shown to work on a lot of problems like the MNIST data set. And I would also like to adjust the dropout, as my model was clearly overfitted to the training data, although I did have a dropout rate of, I think, 0.3. And although these are all valid considerations about the model, I think, again, my first step should probably be addressing problems with the amount of data the model was trained on and the quality of that data. So now for the conclusion. This was a really good challenge to work with such a large data set. I had never done that before, so I learned a lot. My goal was to build a model in TensorFlow that could accurately classify T1 weighted MRI scans as demented or non-demented. My model didn't perform very well, likely because there was not enough data. The data was flawed, and possibly the model was not optimized. I would like to improve performance by creating a TF records dataset, allowing the model to see more data since it will be processed faster, and by tweaking the data and the model. And that's it. These are my sources. Thanks for listening.